Hello, and welcome to an Intro to Sputtering deposition. This presentation is a general intro to sputtering, as well as a tool-specific capabilities list in the KNI lab. This is not a training course on our systems, but rather a very basic intro to help you decide if sputtering is potentially useful in your research. Our lab has two AJA Orion sputter systems. The system on the top left is our dielectric system, which is geared towards sputtering metals, dielectrics, and reactive sputtering to form oxides and nitrides from elemental targets. The system on the bottom left is our chalcogenide system, which is specialized for sputtering tellurium, bismuth, antimony, and selenium-based materials. Reactive sputtering is also possible in this system, though it does lack some capabilities related to this technique when compared to the dielectric system. Both systems are largely very similar. Both are capable of substrate heating to 800C, RF and DC sputtering, reactive sputtering with oxygen and nitrogen gas, and substrate etching. Pressure control, maximum wafer size, and gun accessories are the same in both systems, and the ultimate base pressures are comparable, falling in the low 1e to the minus 9 torr range. The dielectric system has more guns and one centrally located gun for direct sputtering, where the chalcogenide system has 5 confocally oriented guns. While both tools have RF and DC power supplies, the dielectric system is equipped with a pulse DC power supply, which is ideal for reactively sputtering dielectrics. I will go into more detail about confocal versus direct sputtering and pulse DC power in a few slides. For both systems, there are power supplies which have a switch box. This means that one supply outputs to multiple guns at once. However, it can only be connected to one gun at a time. So if multiple guns are connected to a power supply through a switch box, you will not be able to operate more than one of those guns at a time. You can, however, operate them sequentially without moving cables. Both of these systems allow for a very fine degree of process control over magnetron power, process pressures, gas flow rates, substrate temperature, and can allow you to arrange instructions into very complex processes, potentially with hundreds of steps. Now let's look at an example of a basic sputtering configuration. At the bottom we see a diagram which represents the design of one of the magnetron guns in our tools. In this gun, a bias is applied between the anode and the cathode. With a noble gas such as argon present, current is able to conduct through the gas between the electrodes to form plasma. A magnetic array beneath the target focuses the plasma so that the ions head from the anode to the cathode and strike the target surface, thus ablating those atoms away into the chamber to coat the substrate. When using DC power, the target you wish to sputter is the cathode, and with RF power, the polarity between the two oscillates. The anode is then some surrounding shield, which is suspended away from the target by a few millimeters. This shield serves a few purposes in this gun design. One important purpose is to enable the use of what is called a gas injection ring. When used, process gas flows up through the gap between the shield and the target, creating a higher localized pressure right at the target surface when compared to the rest of the chamber. The shield also extends upwards, forming a tube, which is known as a chimney. Chimneys help to contain the plasma and reduce cross-contamination between the guns. Together, the gas injection ring and chimney allow one to operate a gun at lower process pressures than would otherwise be possible. Another benefit of the ring-chimney combo is exploited during reactive sputtering. Reactive gas can be distributed directly to the substrate, while argon is distributed to the target. This allows the target to remain mostly pure metal, while the oxide or nitride forms at the substrate. When sputtering metals, one will typically use DC power, as it requires that the target be conductive. DC sputtering achieves faster deposition rates and sputters continuously. RF power can be used to sputter virtually anything, insulator or conductor, allowing you to sputter glasses, ceramics, and undoped semiconductors. RF sputters in short bursts and generally operates at lower powers, resulting in lower deposition rates. It should also be noted that microstructures can often be seen to differ between films grown in identical conditions when using RF versus DC. Sputtering has pros and cons when it comes to forming and covering patterned features. Due to the amount of argon required to ignite and sustain a plasma, atoms in flight towards the substrate interact readily with the process gas, thus causing ballistic collisions which change their course. As a result, the flux of incoming atoms to the substrate is not normal to the surface. This will cause a much larger degree of sidewall coverage than you would see from evaporating onto the same features. High aspect ratio features will suffer from pinch-off, and sidewall coverage may cause difficulties in liftoff processes. Here you can see a general comparison between the coverage you'd expect with sputtering versus evaporation. Varying the argon pressure during sputtering will affect how direct or how conformal this incoming flux is, with higher pressures causing more conformal coatings and lower pressures facilitating more direct arrivals like what you would see in evaporation. This effect can be utilized to your advantage if you wish to cover the sides of steps. The degree of how conformal a coating is can also be influenced by depositing in a confocal or direct orientation, as shown at the top right. The direct orientation is more suitable when you want to achieve radially symmetric step coverage or to achieve a more directional flux. The downside of a direct configuration shows up when considering uniformity across an area. This plot is actually data for the 3-inch guns in our systems. It shows deposition rate from a direct-oriented gun at distances away from the center of a wafer for different throw distances between wafer and gun. For a distance of 2 inches, there is a sharp rate decline away from this central zone, which is about 2/3 the width of the target. As the substrate is moved farther away, the sharp rate decline smooths out, but so does the maximum achievable rate. The general rule for direct sputtering is that good uniformity is achievable across a substrate with approximately 1 inch smaller than the diameter of the target. But by tilting the guns and moving them far away from the substrate, a 2-inch gun can achieve better than 5% uniformity across a 6-inch wafer. In our dielectric system, there is one central 3-inch gun for direct sputtering. You can move the substrate close to this gun to achieve much higher deposition rates for small substrates. Sputtering processes are controlled by the gases present, their flow ratios, the total pressure, and the power supplied to the guns. Therefore, it is important to understand a basic relationship between these parameters. Our systems are configured so that a crystal rate monitor can be placed very close to the center, where the wafer would actually sit during process. To that effect, we cannot use the crystal to collect a rate and coat our substrate uniformly at the same time. Using the crystal monitor, we can collect data about deposition rates for various power and pressure combinations, and then use that data to plan our process times. This chart is an example of data collected for a 3-inch aluminum target in our chalcogenide system. You can see that as the argon pressure decreases, the slope of the power versus pressure trend increases. That is to say that as pressure decreases, rate goes up. Though this is only up to a certain point. If you continue to drop the pressure lower than 1 millitorr, you should see the rate begin to decrease. You may also start to see unstable plasma or plasma extinguished during the process. It should be noted that for this particular gun, the argon was piped into the gas injection ring. So while the pressure in the chamber was 1 millitorr, the pressure at the target surface was slightly higher, making it easier to sustain that plasma. Sputtering at as low a pressure as possible can be used to achieve a more directional flux, which is closer to what you get when evaporating. But you can only do this to certain limits, as you will lose the plasma and reduce your rate as you continue to drop the pressure much below 1 millitorr. Reactive sputtering can be performed by using a reactive gas during process. Typically, this reactive gas is a minor fraction of the total pressure, with the majority being made up of argon. But sputtering with only reactive gas is possible for certain processes and may be helpful in achieving stoichiometric films and engineering film morphologies. Again, here's a diagram of a sputter gun and a substrate where we are flowing argon into the chamber through the gas injection ring at the gun, and oxygen is directed towards the substrate. This helps to produce a higher argon to O2 ratio at the target surface, and a higher O2 to argon ratio at the substrate. The reactive gas which reaches the target surface may form islands of reacted compounds. If the material is a dielectric or is much harder to sputter than the pure metal, then the sputtering rate can drop substantially. This is known as target poisoning, and it can be reduced by plumbing the gases in separately so that the reaction takes place primarily at the substrate. To the right is an example of an experiment you can do to determine the argon to oxygen ratio, which will result in a substantially poisoned target. To do this, we run the gun in a constant current mode so that the voltage required to maintain it can vary as the target surface properties change. In discrete steps, we sweep the flow ratio from pure argon to some mixture with oxygen and record the voltage. At a certain flow ratio, the voltage will change dramatically, indicating a mostly poisoned target. This kind of experiment can be used to determine the maximum flow ratio between argon and the reactive gas before entering poisoned mode. Notice that this voltage versus oxygen flow trend displays a hysteresis. And so once that poison tipping point is reached, you will need to reduce the oxygen flow substantially in order to go back to a non-poison target. Each of these trends is collected at different absolute chamber pressures, which shows that the poisoning occurs at different flow rates for lower process pressures. The dielectric sputter system is equipped with a pulsed DC power supply. This is particularly suitable for reactive sputtering of dielectrics. During these processes, islands of reacted material can form at the target surface, which can charge up, eventually leading to breakdown to surrounding metallic material. Often these breakdowns cause sudden bursts of rapidly sputtered material in large particles. These particles can be micron in size and result in very non-uniform films. Pulse DC power supplies apply power in short pulses with a slight opposite polarity pause in between. This pause serves to discharge those islands, preventing them from arcing. The figure at the top left shows that for the aluminum oxygen system, the pulsing duty cycle does not affect when a target will poison. This makes sense, as it should be only dependent on oxygen partial pressure and pumping speed. Another interesting test involves collecting a poisoning hysteresis with total flow rates of the gas mixture as a variable. In these tests, the fraction of oxygen flow for each step is kept the same, the process pressure is kept constant, and the same number of steps is made for each sweep from pure argon to some defined oxygen to argon ratio. What this shows is that you were to keep the oxygen flow at 25% of the argon flow. By reducing the total flow, you can shift when the target will poison. This is also just another way to show that pumping speed is a dominant factor in the oxygen fraction required to poison a target. A higher flow rate results in poisoning at lower oxygen percent. This can be explained by reasoning that with lower flow, the rate at which oxygen is consumed by the reaction becomes higher than the rate at which oxygen is introduced, thus limiting the rate at which islands can be formed on the target surface. It's probably wise to operate at a flow rate which allows target poisoning at a low oxygen fraction, but to remain just shy of poisoning the target. This way you can ensure that there is sufficient oxygen, but not so much that you dramatically reduce your sputtering rate. Note that these behaviors will differ across different metal and reactive gas combinations, but in general should hold true for most oxide nitride systems. Let's go over a simple example of a sputtering process. If you're writing an automatic process, you will probably want to structure it into two layers. The first layer is where you will strike the plasma at the target. Start by setting your flow and pressure appropriately to strike. A good standard for our tools is 30 SCCM argon flow, 30 millitorr chamber pressure, and 30 to 50 watts on the gun. If you are striking plasma on a dielectric, a hard or brittle material, or a target bonded to a copper backing plate, it is wise to strike at 20 watts or less. Then enable power output to the gun and wait a few seconds for the plasma to stabilize. In the second layer, you will reduce the pressure and flow to what you will use during process, then gradually ramp the power to the desired value. Be careful not to exceed the recommended limits for the target. This info is posted on the system. For metals, you can ramp up at a rate of 100 watts per 60 seconds. For dielectrics, you can ramp up at a rate up to 10 watts per 60 seconds. Typically, once the target is at the desired power, a pre-sputter is performed to clean and condition the target prior to opening its shutter. This is generally performed for 60 seconds to a few minutes, after which, open the shutter to begin coating the substrate. When finished, the process reverses. Close the shutter, ramp down power, cut gas flow, and fully open the valves to the pumps to go back to high vacuum. While there's a very large number of possible processes you could come up with using these tools, this example shows a very different capability from our existing evaporators, which I think is important to introduce, and that is the ability to create concentration mixtures and gradients in thin films. This process shows 5 layers. The pink and green trends display the power of 2 separate sputter guns. Let's say that each gun is sputtering a different material. First, we would ramp up the power of each gun individually to a desired power. We opt to keep our shutters closed during this layer so that no material is deposited on our substrate. Then we would open both shutters for some amount of time, depositing a layer with composition A, which is some mixture of the 2 materials. Then we would close the shutters, ramp each gun to a new power so that the deposition rates of each material switch, and then after that the shutters would open for a second deposited layer, where the ratio of the 2 elements have switched, giving us a stack of 2 different mixtures. You could, for example, also leave the shutters open during layer 3. While the powers are ramping, you'd make a composition gradient across its thicknesses as the rates swap with each other during the ramp. Very many variations of this basic idea can be done. During sputtering, there's a number of common issues you may encounter. Probably the most common of all is that you struggle to ignite a plasma. In general, it's wise to try striking a plasma manually before trying your recipe, or at the very least to test out your recipe manually before writing it into an automatic one. Common reasons for this are localized gas pressure is too low, chamber argon pressure too low or high, or a poison target. To deal with local gas being too low, you can try to briefly open the shutter. Often a stubborn gun will ignite the moment the shutter opens. You can then immediately close it and the plasma will likely remain lit. Another technique is to strike a gun next to the desired one. The nearby energetic ions will assist in lighting the plasma of the gun you intend to use. Also, if you are planning to etch the substrate prior to deposition, making an auto process that strikes the desired guns while the RF pre-etch is happening will assist in the formation of plasma at those guns. The main reason for this striking difficulty comes from the path for letting gas get to the target surface. If it's too constricted, it can be problematic and too hard for the plasma to ignite. Usually a shutter should be positioned so that when it's closed, it hovers a few millimeters above the gun. If it presses flush against the gun's opening, it can restrict gas flow. Flowing gas in through the gun itself also greatly helps reduce this problem. If you think you have a poison target from a previous run, you can swap an RF cable to one of the guns you're trying to use and sputter with RF for a few minutes to clean off the oxide or nitride film on the target surface. You should then be able to use DC without issue. Plasma loss during process can be caused by a few things. If you put too much power into a target, it will start to heat up faster than the gun's water cooling can match, resulting in a climbing target temperature. If the target gets hot enough, it will degauss the magnetic array underneath it, which can cause you to lose the plasma. This is often just slightly degaussing the magnets, but it can permanently ruin them if you do it enough or if the target does get too hot. Make sure you are always staying beneath the maximum power density for the target. Also, always be sure to ramp the power appropriately for the target to avoid cracking brittle targets. Flaking material from nearby coated parts can also cause shorts between the anode and cathode, which can cause plasma loss. If you lose the plasma, it's wise to wait a few minutes and try to strike it. If it won't strike, then it should be assessed by KNI staff. If you're doing reactive sputtering, arcs caused by charge buildup on a poison target can also cause plasma loss. If you're trying to make dielectrics, using pulse DC power can greatly reduce the chance of this. When you're trying to ignite the plasma and you see periodic flashes, as if the plasma is igniting and extinguishing rapidly, you probably have a poison target. Try RF to clean it. This happens because the surface of the target is essentially charging like a capacitor and then discharging. Another possibility is that the target was installed improperly. It's unlikely that you'll experience this because the connection is tested every time a target is exchanged. This table is a pretty good and succinct comparison between a few deposition techniques. It's pretty self-explanatory, so I recommend you simply pause this video and study it as you like. For more information, look up the source provided. This presentation serves to give you a very qualitative look at sputtering. If you wish to get more into the fundamental equations, models, and physics of sputtering, I recommend these two books. The Handbook of Sputtering is a very general book which covers sputtering broadly from early to modern methods, as well as the fundamental physics. The book on the left also covers fundamentals, though spends less time on them, instead focusing on reactive sputtering of oxides and nitrides, and it pulls a lot of information from actual studies where they synthesize these compounds. If you haven't seen it, the Lesker materials deposition chart is a very big, very comprehensive list of recommended methods for evaporating, sputtering, or otherwise depositing different materials. The link at the top left will take you to it. I also get a lot of questions about what materials can go in our chambers. For that, you should take a look at outgassing.nasa.gov. They have a list of low outgassing materials, and if you can find your material on that list, then it's safe to put it in the chamber. Thanks for watching. If you have questions, you can email me at the email address shown.